Okay, we'll get started. So, your first homework assignment was due on Friday. The chapter 1 homework is due on Thursday, the 29th. The chapter 21 homework is due on Thursday, the 5th. Both of these are on WebAssign. You can request an extension on any past due assignments. I think someone's already done that. Though if you do request an extension, there is a 10% penalty. There is a lab today. We'll be doing our second lab. If you haven't turned in the first lab, it is due today. I think everyone has though, so we'll just continue on. So we'll start with our lecture. So we were discussing plate boundaries. So the Earth's crust, the most active areas of the Earth's crust are at these boundaries between these tectonic plates, these large rigid plates floating on the ionosphere. Tectonic plates have crust. The crust is made of two different types. There is continental crust, which is primarily composed of more silica-rich minerals, which gives it a lower density than oceanic crust. It is roughly granite-like. Most of the rock is something similar to granite. That'll be relevant in the lab. Oceanic crust is primarily composed of magnesium iron-rich basaltic rock. It is similar to basalt, which gives it a higher density than continental crust. Continental crust is about 2.7 grams per cubic centimeter. Oceanic crust is around 3.0 grams per cubic centimeter. And that does mean when continental crust and oceanic crust meet, the oceanic crust is denser and will be the one that sinks. Name? Coral. And sorry. Ah. And sorry. Coral? Oh, Noah. Okay. Sorry, I was looking at first names. I've never been given first names. So there's three different types of plate boundaries. You have divergent boundaries where plates are separating. Name? So the most common form of divergent boundary is at mid-ocean ridges because, well, given enough time, any divergent boundary will become a mid-ocean ridge. Because if you start on continental crust, eventually a divergent boundary will separate enough to tear a gap that will flood with water and become a sea. That's like how the Red Sea formed. If you've seen these very linear seas like the Red Sea, that's sitting on top of a divergent boundary. Convergent boundaries are where two plates are driven together and one plate is consumed. The plate that gets subducted and consumed is always an oceanic plate. And then transform boundaries are boundaries where two plates slide horizontally past one another. You tend to get lots of earthquakes there. But crust is neither created nor destroyed. Underneath the rigid lithosphere that makes up the plates is a higher temperature layer called the ionosphere. This layer, though it's basically solid, is so close to its melting temperature that it's relatively plastic and deforms, especially over the long time periods of geologic time. So the ionosphere is much more easily deformed than the lithosphere. And you can view the lithosphere as floating on top of the ionosphere. It functions very much like it's floating on top of the ionosphere. Everything's just a little slower. We see similar things with ice on top of water. You get similar effects to what we see with tectonic plates. And because the lithosphere is floating on top of the ionosphere, there's this idea of isostasy. Anything that's floating in a liquid will rise up and down to make sure that its mass matches the amount of liquid the mass of the amount of liquid it displaces. That's why if you put a block of wood in the water and it floats, it's partially submerged. So if it has buoyancy, it will balance out at certain height. So continental plates will float higher up because they're less dense. Less dense things will float higher up will float higher up. And at any given time, all the plates are more or less in isostatic equilibrium. Some places we have places where things are recovering to isostatic equilibrium. They're floating back up. For example, the Hudson Bay area is currently rising up because at the end of the last ice age, the glaciers retreated, removed a whole bunch of weight from on top, and so now that whole area is rising back up because that weight was removed. And mountain ranges represent very thick masses of continental material. They both go up higher, but they also go down lower. Their root is deeper as well. And that's why they float higher. So, for icebergs, for example, 89% of an iceberg is always going to be submerged. So, it's got bigger on top, then it's going to be bigger underneath. Similar effect with crust. At mountain ranges, it is higher on top, but it's also got a deep root. Now, plates move. We can directly measure that these days. It's on the order of inches to centimeters, a couple centimeters a year. They don't move fast. But it is due to forces. The forces that drive this movement are forces in the atmosphere, in that more plastic, more mobile layer underneath the plates we live on. And it's generally thought that it's driven by convection cells. When you have warm material rising and cool material sinking, you get cycles. This is convection. It drives lots of things out in the world. We'll talk about it more when we get to weather. But, just if you're in a room, if you have a radiator on one side, warm air will rise from the radiator, will travel across the room and will sink on the far side, and you'll get a convection cycle. Similar things happen where warm magma rises, reaches the surface, travels along, and cools and sinks, and there's a cycle. And that cycle drags the plates above it along. There's debate about how those cycles are organized, whether they're giant cycles going down all the way to the upper core, or whether there's layers of cycles. There's big, slow cycles and then smaller, faster cycles above them. That's not known. But it's generally understood that unequal temperature distribution in the atmosphere and upper mantle leads to the hot, less dense material rising and cooler, more dense material sinking. These cycles move the atmosphere, and that drags along the plates above them. Similar cycles like this of rising and sinking material are also the source of the magnetic field of the Earth. Those are cycles in the liquid metal core. So because of these convection cells in the atmosphere, you get drag from this more active atmosphere, drives the outermost solid lithosphere. Additionally, at spreading ridges, the new material gets pushed up and slides down slightly. And when a plate subducts, it's pulled down by gravity. So let's talk about the individual types of boundaries. The divergent boundaries, the most common version of these is the mid-ocean ridge system. These represent a zone where two plates are moving apart. So when two plates separate, magma can well up into the gap, and the initially molten magma gets shouldered to each side of the rift, and that causes the lithosphere plates to slowly separate. You get liquid magma comes up and it sort of pushes the plates apart a little. And then drag from the underlying lithosphere keeps the plates in motion. So you get material pushes up, it can sort of slide out to either side, and then drag from the underlying lithosphere keeps the plates in motion. And as the two plates move apart, new magma will well up and cool along the rift zone, and this creates new crust. And as the magma cools, it gets denser, and that also helps pull it to the side. Older oceanic crust is denser than younger oceanic crust because it's cooled down more. As a portion of the plate moves away from the hot spreading center, it cools, it contracts, it becomes more dense. And due to this increase in density as it goes away from the spreading center, the plate will gradually sink and the oceans will grow progressively deeper. So you get a ridge where you have the less dense material that is just formed. And then as it spreads apart and cools, it sinks down a little. So that's what is happening at the Mid-Atlantic Ridge. So here's a video about the Mid-Atlantic Ridge, if it will successfully load.
But while some plates crash together, others tear apart. But while some plates crash together, others tear apart. It happens under the ocean, like here, in the middle of the Atlantic. Lava erupts at the boundary between two crustal plates, sealing the tear. This is the Mid-Atlantic Ridge, a 10,000-mile tear on the floor of the Atlantic Ocean. The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed. It stretches from the South Atlantic all the way to Iceland in the north, where it rises above sea level. From the air, the Mid-Atlantic Ridge is an awesome sight. This dramatic scar in the landscape marks the boundary between the North American crustal plate on the left side and the European plate on the right. The gap between ocean plates is filling in at a rate of an inch a year. Part of the restless movement of the Earth's crust that's reshaping our world.
Well, that's the Mid-Atlantic Ridge, where you have a divergent boundary that is in continental crust, like you can see with Iceland. It basically tears that apart, right? Like in Iceland, it's also happening in the East African Rift Valley. That's a place where that's also a divergent boundary. So, you get these things about you can touch two continents in Iceland. There are much easier places to get to in the US. You could be on two continental plates. You can go to California and stand with one leg on the North American plate and the other leg on the Pacific plate. Because the San Andreas Fault, which is the separator between those two plates, just runs through the middle of California. So that's a divergent boundary. A convergent boundary is where two plates are coming together. And there are basically three possible combinations, because there are two different types of crust. So you can either have oceanic and oceanic crust running into each other, oceanic and continental crust running into each other, or continental and continental crust running into each other. Those are the three possibilities. When you have oceanic crust running into oceanic crust. One of the oceanic plates will subside under the other. It will melt. You'll get a string of volcanoes. You get chains of islands. This is places like the Aleutians in Alaska, the Marianas. There's an associated trench when one oceanic plate sinks under another. The Marianas, where you may have heard of the Marianas Trench, Japan, places like that. A lot of the ring around the Pacific Ocean are island chains caused by oceanic convergent boundaries. When you have oceanic continental convergent boundaries, well, the continental plate is less dense than the oceanic plate, so the oceanic plate is always the one that subducts underneath the continental plate. The classic example of this is the west coast of South America and the Andes. You get volcanoes that form mountain ranges. So the Andes mountain range along the west coast of South America is caused by continental oceanic convergent boundary. Similarly, the Cascade Mountains in the Pacific Northwest are a similar situation. There's a small plate there that is going underneath the North American plate. And then lastly, you can have a continental convergent boundary. This is the only case where at a convergent boundary where crust is not destroyed. Basically, you have two continental crusts. They're too thick and light to sink, so they just pile up and form the biggest mountain ranges possible. This is happening in the Himalayas, where India is slamming into Asia and piling up the Tibetan Plateau and the Himalayas. It's also how the Appalachians formed some 300 odd million years ago, or maybe older than that, because they formed in the initial formation of Pangaea. There are other similar mountain ranges like this. It's also like how the Alps formed. And if you have an oceanic plate involved in your convergent boundary, it will subduct, or one of the two will subduct. So anytime you have an oceanic plate, you get subduction. And that's where one plate descends underneath another, sinks into the atmosphere, and eventually melts. And this occurs at what's known as a subduction zone. So the first type is an oceanic-oceanic convergence. That's where two oceanic plates collide. They have essentially the same density, 3 grams per cubic centimeter. One of them is likely to be a little bit denser than the other because of just natural variation, probably the older one. One will eventually end up subducted into the other. It's a little bit of a crapshoot, but it is likely to be the older plate that gets subducted. And you get long, narrow, deep sea trenches at the plates where that plate is subducted. So an example of this is the Marianas Trench, which has the Challenger Deep, which is the deepest point in the ocean. It's like 12 kilometers deep, roughly. It's legitimately hard to measure how deep it is. And then as the subducted plate comes in contact with the aethnosphere, it begins to melt. Some of the material melts out of it, that rises up and forms a volcanic island on the overriding plate. And this is how lots of volcanic island chains form. Not all, there are exceptions like Hawaii. But a lot of these arcs of volcanoes are caused by this process. So here you have lithosphere sinking, you have aethosphere rising up, and you get a volcanic island on. And you can have some pretty dramatic earthquakes where one plate is subsiding under another because you have that big, shallow thrust fault that has a lot of area to stick on. So when it releases a lot of energy. So the deep sea trench and the volcanic island arc will be parallel and close to each other. And eventually that volcanic arc will form new continental crust. So here's a short video about oceanic trenches with the example of the Mariana Trench. So here are the Mariana Islands.
If we remove the ocean water around the islands, the collision is revealed on the sea floor. The plates come together just east of the Mariana Islands. By looking beneath the seafloor, we have an even better view of the colliding plates. The collision formed a deep canyon near the islands. This is the Mariana Trench, which bottoms out at 36,200 feet below sea level, the lowest spot on Earth. Mount Everest would easily fit in the trench, with over a mile to spare before reaching sea level. Plate tectonics is driving the two plates together at the rate of a few inches per year. The plate on the right, which is the heavier of the two, is sinking below the lighter plate. This is called a subduction zone. As the plate sinks deeper, it melts. Magma is created, which can force its way up through the plate above. Volcanoes erupt on the sea floor. Eventually, they might become islands, like Pagan and Anataha.
So I actually made a mistake when I was speaking earlier about the Mariana Trench. It's not 12 kilometers deep, it's only 11 kilometers deep, but it is legitimately hard to measure the depth. But it is about 11,000 meters. So if you have a continental oceanic convergence, continental crust is less dense. The oceanic crust is what will always subduct. So if you have a subducting plate, it's always oceanic crust. You get a trench along the zone where the oceanic crust subducted. And then again, as the oceanic crust descends from the atmosphere, it begins to melt. The big difference is that instead of rising up to hit the ocean floor, it rises up to hit continental crust. And you get volcanic mountain ranges. And so examples of volcanic mountain ranges are the Andes and the Cascades. For a little more complicated thing caused by this sort of subduction is the Rockies, which were actually caused by folding caused by subducting plate. So what happened to the Pacific plate subducted under the North American plate, but it ended up, instead of sinking down, it ended up running really shallow, and it caught material further inland, squished it, and folded it upwards to form the Rockies, which is what this short video is about. The Rockies are sort of have a weird form of mountain formation because they didn't form where mountains normally form. Because they're not close to any.
On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. The granite mountains here have been pushed up 4 miles. On top of the granite lie spectacular red slabs of rock known as flat irons. They're the patchwork remains of sedimentary rock that once blanketed the entire granite basement. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion year old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
So, out of oceanic continental conversions, what you usually get is oceanic crust sinking, some partial melting, and what you get volcanic mountain chains, like the Andes and the Cascades. The ocean trench and the volcanic mountains are parallel and close to each other. That's why you get this very sharp drop off on the west coast of South America. It's very steep up into the mountains. Now, when two continental plates collide, they're both basically too light to subduct, because they have a relatively low density of around 2.7 grams per cubic centimeter. The subduction of continental crust is minimal because they're both less dense and thicker. So during convergence, instead of one sinking, the two plates just basically get intensely deformed, folded, faulted, and piled up to form mountain ranges. They construct fold mountain ranges. And continents can increase in size during this process by basically gluing themselves suturing themselves together along fold mountain systems. The most dramatic of these currently is the Himalayas, which is still in the process of growing as the Indian subcontinent slams into Asia, and it is pushing the Himalayas up even higher. So you'll find at the top of the Himalayas material that was in the ocean between those two continental plates that got scraped up and piled up. So the top of the Himalayas are topped with marine limestone. So this is a short animation showing the process of the mountain building of the Himalayas. You can see first you get movement where there's oceanic crust, and then you run out of oceanic crust. The two continents hit each other. They start to pile up, they fold, they vault a little, and they push up that material from in between to form the Himalayas and the Tibetan Plateau. So what you get is you get continental crust running into continental crust. It folds, buckles, faults, piles up to form a mountain range. Examples are the Himalayas, the Alps, and the Appalachians. The Appalachians is a very old one of these. It formed hundreds of millions of years ago when Pangaea formed. It's from when it's from that initial closing of the Atlantic Ocean, the proto-Atlantic Ocean that formed Pangaea, and then they separated apart again. And the last form of boundary is a transform boundary. This is where two plates are sliding past each other, and then either driving into each other or spreading apart. And this is a zone of shearing or transform motion. And the crust is neither destroyed nor created along a transform boundary because neither subduction nor magma upwelling occur. You just get grinding along these faults in earthquakes. So these zones are said to be seismically active. You get periodic movement along these faults. You get a sudden energy release. So the most famous of these is the San Andreas Fault in California because it's very long and impressive, and it runs through the middle of a rich country. Another one, there's one in Haiti, running along the edge of Haiti, parallel to the coast there, that is some devastating earthquakes. And here's a short video about the San Andreas Fault, showing some places where you can see the movement of the plates and also some other things.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California, the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with 1 foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Billam keeps track of these changes with his creep meter. a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
Here's a summary of the discipline boundary. For the divergent boundary, you have a spreading motion. This is constructive. You get oceanic lithosphere created. You get a ridge or a rift, and there is volcanic activity. At a convergent boundary, you get subduction. It's destructive. Oceanic lithosphere is destroyed. You get a trench, and there is usually volcanic activity. And at a transformative boundary, it's lateral sliding. It's conservative. Lithosphere is neither created nor destroyed. It has no major effect on the surface, and there isn't any volcanic activity, but you do tend to get earthquakes. Now, at plate boundaries, you tend to get volcanoes. The term volcano can refer to either a vent, a hole in the ground which hot molten material escapes, or a mountain formed by that material, that solidified volcanic rock. And although the specific occurrence of volcanic activity is usually unpredictable, you never quite know when something's going to go off. The locations of eruptions and potential eruptions is known. We can study volcanoes to sort of get an idea if they're due, look at the pattern of eruptions. Unfortunately, it's easier to predict the eruptions on the volcanoes that erupt more commonly and more peacefully than the ones that erupt less often and more violently. But you can get an idea of things possibly being due. So here's sort of a map of the active volcanoes of the world. You can see that pretty much all the active volcanoes are on plate boundaries. All these volcanoes are sitting along plate boundaries with a few exceptions. So the big exception is here is the active volcanoes in Hawaii. They're sitting over a magma hotspot where hot magma is rising up from underneath and causing volcanoes on the plate above. And yeah, and that might be similar over here. I'm not entirely sure on everybody. There's a few hotspots out there, but not all of them have active volcanoes. So most volcanoes occur along convergent boundaries because when 2 plates collide, one plate gets subducted beneath the other. And during that subduction process, the rock above the subducting plate margin melts and the molten rock rises to the surface to form volcanic islands or mountains. You also get lots of volcanoes at divergent boundaries, but they tend to be underwater. So we don't talk about them as much. So the most famous volcanoes at divergent boundaries are in Iceland. The Iceland volcanoes are at a divergent boundary. But most of the volcanoes we talk about are at convergent boundaries. So the ring of fire around the Pacific Ocean is mostly these convergent boundaries around the edge of the Pacific Ocean, forming all these volcanoes. There's plenty of underwater volcanoes as well. So here's a video about those underwater volcanoes in the ring of fire.
There's another world beneath the ocean's surface. Come join us as we explore the depths below. Orange and red flashes in the pitch black. Lava oozes from the cracks and rolls across the ocean floor. Earthquakes rumble and roar as tectonic plates grate against each other. We're at the rim of the Pacific Basin. Because it is one of the most geologically active places on Earth, scientists have nicknamed the area the Ring of Fire. The movement of tectonic plates has created a nearly continuous series of oceanic trenches and chains of volcanoes stretching for 25,000 miles. The Ring of Fire is home to hundreds of volcanoes, but most remain hidden far below the water's surface. In fact, 75% of all volcanic activity on the Earth happens in the ocean. But the effects of all this activity aren't felt only in the Pacific Basin. Earth's ocean and geology are global interconnected systems that can affect us all. Tsunamis can be generated by underwater earthquakes, volcanic eruptions, or landslides. And as we have seen, their impacts can be devastating. Undersea volcanoes produce chemicals and heat that affect the ocean environment. We need to better understand these natural inputs as we increasingly introduce our own with man-made pollutants. We've only recently begun to explore the hundreds of volcanoes rising from the ocean floor that make up the Ring of Fire. Over the last few decades, several expeditions to the western Pacific Basin have been conducted. Using the latest mapping and robotic instruments, researchers have learned more about the geologic activity at these sites and the marine life that thrives on hydrothermal vent systems. But learning new things often leads to more questions, which means there's still a whole lot more left for us to discover. So join us as we continue to explore the depths below.
And the life around hydrothermal vents is particularly interesting because it's thought that those are the conditions that possibly led to the first evolution of life. And it's also thought that conditions similar to that around hydrothermal vents exist in many other places, in other places in the solar system. So that's one of the places we might look, places that have hydrothermal vents are places we might look for life elsewhere in the solar system. Because life around hydrothermal vents functions without, it gets its energy chemically from the hydrothermal vent and not from the input of sunlight, like most life on the surface. So here is an example of the subduction of oceanic lithosphere forming a volcanic island arc. This is Japan, the subducting Pacific plate under the Eurasian plate forms the volcanic island arc of Japan. Similar processes happen all throughout the oceans. And that's how you get these large arcs of volcanic islands. Now, earthquakes are a sudden release of energy due to a sudden movement of the Earth's crust or mantle that results from the release of stresses. And the study of earthquakes is called seismology. And earthquakes cause the Earth's surface to vibrate and sometimes result in violent movements depending on the amount of energy released. So every day there are hundreds of earthquakes, but they're generally too small for humans to feel. They're not a big deal. It's the big ones that are a problem. But they can be detected, and we do detect them, and we use them. We study them. So earthquakes occur when rocks grind past each other along plate boundaries. Anytime rocks are moving alongside each other, they have friction, they'll stick, and eventually they will build up enough strain and to overcome the friction, and build up enough stress and strain to overcome the friction, and there will be a big release of that stress in a sudden process. And in that process of release, you get vibrations that radiate out in all directions from the point of disturbance, the point where of first release. And that major danger from earthquakes is not really the vibrations themselves. If you were standing in a big open field during even a pretty severe earthquake, you'd probably be okay. It's that they cause human-made structures to collapse. That's the biggest issue. The problem is not that the ground is shaking, it's that the roof falls on your head. So, the problem is that, the ground shaking causes the building you're in to collapse. That's bad. It can also cause fires and other damage, which can, lead to other sources of damage. So most earthquakes are caused by movements of the lithospheric plates. They can also result from explosive volcanic eruptions, human-caused explosions. Fracking causes small earthquakes, for example. So we can make earthquakes, but the primary source of earthquakes is the movement of lithospheric plates, and they're sliding at faults in the crustal material. And a fault is really just a crack in rock where the two sides have moved. So a fault is any fracture in rock as along which there has been visible movement of the two sides relative to each other. So there are faults all over the place. They're very common, but lots of faults are just little, not a big deal. It's the big movements that can cause significant earthquakes. So here's an example of a fault. You can see we have layers of rock. There's a crack along here, and the two sides have moved relative to each other. This side went down, this side went up. So that's a fault. And you can see, because these are sedimentary rocks that were laid down in layers, you can see how this layer used to be continuous, this sort of light layer, and how this side has moved down and this side has moved up. Now, earthquakes are most likely to occur at plate boundaries, because that's where we have two big plates sliding next to each other. So when you have two plates moving, they have stresses exerted on the rock formations and adjacent plates. Because rock possesses elastic properties, it bends. That stress will lead to a strain, a bending, or a distortion, and energy will be stored until the stresses can overcome the friction between the two plates, at which point there will be a sudden release of that stored up energy. As the plates suddenly move, that energy gets released. It travels outwards in vibrations and waves, and that causes an earthquake. Now, earthquake occurrence generally follows the borders between plates. You look at where earthquakes occur, they correspond pretty strongly to plate boundaries. There are exceptions. So there's a handful of earthquakes in the middle of the US. You get earthquakes out in Hawaii. You do get earthquakes elsewhere, but most of the time, earthquakes occur near plate boundaries, as you can see. And there's a lot of earthquakes around the Ring of Fire and the Pacific Ocean. And generally, after an earthquake, you will get aftershocks. These are smaller earthquakes as material settles into its fully relaxed state. They're continuing to adjust to their new position. Now, transform boundaries are often the source of some of the world's largest continuous faults. These are transform faults. The San Andreas Fault in California is a transform fault that lies between the Pacific and the North American plates. You get some big earthquakes there. Now, the biggest recorded earthquakes have not been at transform boundaries. They tend to be in, you get some really nasty ones at thrust boundaries where one plate is sliding under another. There's a lot of area there. So you can get, and you can also have, unfortunately, big earthquakes that cause tsunamis, which are really devastating. So the San Andreas Fault of California, it's the master fault of an intricate fault zone that runs along the coastal area of South and Central California and all the way up into Oregon, where it travels into the ocean. And lots of earthquakes have occurred along this fault. And in 1906, there was a major earthquake in the San Francisco area. This resulted in hundreds of lives lost and millions of dollars of damage. And as a weird side effect of this, the modern version of Chinatown that you see, that has all the pagodas and stuff, that happened as a partially due to the fallout of this earthquake, because one of the things that happened after the 1906 earthquake is the firefighting in San Francisco after that earthquake was biased towards rich white areas. Let's put it that way. Another example, in 1989, a major earthquake in the area caused severe bridge building and highway damage. Things collapsed. There's nothing you can really do to control a fault line. There's no way to release the energy more slowly. What you can really do is work to design your buildings and structures so that the damage is reduced. So if you design your buildings and structures so that they're not as affected by the shaking of the earth, or you design your infrastructure so that it, for example, once an earthquake starts, it shuts itself down, so you don't have, broken gas lines releasing flammable natural gas everywhere, or broken water lines causing subduction, flooding and subduction. Liquefaction and things. That can help. So, for example, technologies have been developed in places with lots of earthquakes, like Japan, to do things like shut down all the water lines and gas lines the moment they detect the first vibrations of an earthquake, so that you don't get additional damage from those broken lines. And also you can design your buildings to be resistant to earthquakes, so that they can shake and not fall down. So here's the San Andreas Fault. So Baja California and the coastal parts of California are steadily moving north compared to the North American plate. And so in about 10 million years, Los Angeles will move far enough north to be next to San Francisco at the rate that they are moving. And so the San Andreas Fault goes in I can't remember what this little strip is, but a little bit of ocean in between Baja California and mainland Mexico, and then it exits into the Pacific Ocean in Oregon. So when you have an earthquake starting, there's some point underground on the fault where it starts slipping, it starts moving. That point of initial movement or energy release along the fault is called the focus. It is also sometimes called the hypocenter, but the term that we'll be using is the focus. The focus is generally located underground, and it can be a few miles to perhaps several hundred miles deep. Now, the point on the surface directly above the focus is the first point we see earthquake waves at the surface. It's the point, if we're just considering the surface, the earthquake seems to emanate from. That point on the surface is called the epicenter. This is the surface position that receives the greatest impact from the earthquake, because the energy is released from the focus. It's traveled the least distance to reach the epicenter, the closest point on the surface. So it hasn't spread out as much, so you get the biggest waves there. Now, that doesn't necessarily mean that it's the place that gets the most damage, because a lot of how much damage occurs in an earthquake depends on things like what the ground is made of, what the buildings are made of, things like that. But it is the point that it's the greatest impact, largest waves from the earthquake. And to locate the epicenter, we can use a process called triangulation. So the nice thing about earthquakes is that they have waves of two different types that travel at two different speeds. So if you measure the difference in time between those two waves, you can figure out how far away the center of the earthquake was. And if you do that from three different places, you can do what's called triangulation and find the location of the earthquake center, epicenter. So here's a short video about how epicenters are located.
Okay, so let's take a look at how to locate the epicenter of an earthquake using the triangulation method. All right, so here is a map of the world, and we're going to zoom in on a particular region. We'll look at North America, and let's imagine that there was an earthquake somewhere in North America. Well, the question arises, where was the epicenter of that earthquake? Now, we may be able to get a general idea of where the epicenter was based on looking at the severity of damage, eyewitness reports, etc. But if you want to pinpoint the actual location of the epicenter, you have to do some calculating. And so let's look at how we're going to do that. First off, in order to pinpoint the epicenter, you need a minimum of 3 seismic stations. So let's pop a few of these seismic stations on the map. Let's say we have one here in California, one up here in Canada, and one down south here, labeled 1, 2, and 3. Now, these are locations where we have seismometers actively monitoring the shaking in the Earth's crust. Of course, we have seismic stations all over the world. In order to use this triangulation method, we need at least 3 of these, or data from 3 of them. So, step 1 is going to be to take the data, the seismograms from each of these stations, and determine each of their epicenter distances. That is to say, I want to know how far point 1 is from the earthquake, how far point 2 is from the earthquake, and how far point 3 is from the earthquake. And this is fairly easily accomplished. You would simply find out the difference in arrival times for the P waves and S waves, and then use a travel time graph to calculate the distances. So let's say you have done that, and you have established that seismic station 1 is approximately 700 kilometers from the earthquake. So something like this. But the problem is, we don't know if it's 700 kilometers in this direction, in this direction, in this direction. We don't know. It could be 700 kilometers in any direction. So what we can do is draw a circle around point 1 with a radius of 700 kilometers. And now we know that the epicenter is somewhere on that circle, somewhere on that line. But again, that's not good enough because we want to pinpoint the location. So let's turn our attention to location 2 and say we did our math and we found that location 2 is 3,000 kilometers from the epicenter. Now again, it could be 3,000 kilometers in any direction. So we will draw a circle around point 2 with a radius of 3,000 kilometers. Now notice something. If you did this properly, your circles should intersect, most likely in 2 places. And what that means is that the earthquake had to happen either here at this intersection or here at this intersection. But again, that's not good enough because we want to know exactly where the epicenter was, which leads us to station 3. We take our seismogram, we do our math, and we determine that station 3 is approximately 3,500 kilometers from the epicenter. So, again, it could be in any direction, so we take a drawing compass and we draw our circle with radius 3,500 kilometers. Now, if this works out properly, all 3 circles should intersect in one single point, and that point is your epicenter, shown by the pink star. This is what we call the triangulation method for locating the earthquake epicenter.
So, just sort of a general idea, the focus is the point underground where the earthquake starts. The epicenter is the point on the surface immediately above the focus that gets the biggest waves. That triangulation method is used in a lot of things. If you've ever used GPS, GPS uses triangulation from satellites in orbit around the Earth to do a similar thing. It's a little more complicated because figuring out how far away the satellite is a little trickier, which is why it ends up taking 4 satellites. But yeah, uses triangulation. Lots of things use triangle. So earthquakes release energy, and when the earthquake's energy is released from the focus, it propagates outward in all directions as seismic waves, which can be measured with a seismograph. And a seismograph is just like a setup that measures how much the earth vibrates. It monitors and measures the seismic waves. And the greater the energy released in the quake, the greater the amplitude, the height of the traces or lines on the recorded seismograph. And that's how we classify earthquakes. We classify them based on basically how big the waves they generate are. So if you've ever heard of the Richter scale is a scale based on the size of the largest seismograph wave, the original version. The modern version is a little bit modified because it turns out for really big earthquakes that sort of saturates. And so there's some corrections you need to take into account, but more or less the same thing. So a seismogram is really just some object that is weakly tethered to the ground so that when the earth moves, it stays in place and leaves behind a recording of the movement on something like a rotating spool with photographic paper and a light beam, or it could be with a pen on paper, things like that. So the idea is that here's an example of a seismograph. So during the quake, the spool will move up and down. The light source will not move because it is not strongly coupled to the bedrock. The spring lets it effectively stay still. You put a heavy weight on this so it doesn't move. The light beam is relatively still, and you get a recording of the movement of the earth. And the severity and strength of earthquakes get measured on two common scales. So the Richter scale measures how much energy is released during a quake by calculating the seismic wave energy at a standard distance and based on the height of the largest. It was originally based on the height of the largest seismograph wave, and then it was slightly modified because it turns out for really big earthquakes, you get energy spread out over more waves, kind of thing. Basically, the biggest wave stops getting bigger because the earth only moves so much. It needs a little bit of modification, but it's not a huge difference. And the modified Mercalli scale describes the results of the earthquake in terms of felt and observed effects. So the Richter scale is a quantitative measurement of how much the ground shakes. The modified Mercalli scale is a measurement of what damage is done. So the Richter scale was developed in 1935 by Charles Richter of Caltech. The most common earthquake measurement. If you hear people talking about earthquake magnitude, they're talking about the Richter scale or the modern version of the Richter scale. And it correlates the largest seismogram peak during a given quake to the amount of energy released by the quake. And again, it turns out for very big earthquakes, this needed to be slightly modified, but that's not an issue for this class. And the Richter scale gives the earthquake's magnitude expressed as a number. And if we're talking about an earthquake, it's going to be a number between about 3 and 9. There's only been a handful of recorded earthquakes that are bigger than 9. Those are giant, awful, massive earthquakes. And earthquakes below 3 we don't talk about because we can't really feel them. They're recorded, but no one talks about earthquakes that you can't feel. And the thing about the Richter scale is that it is logarithmic. So every whole number increment represents 10 times as big movement of the earth. And a 31s, it's almost 32-fold increase in the energy that is released. So an earthquake of magnitude 5 will release like 31, 32 times as much energy as an earthquake of magnitude 4. And an earthquake of magnitude 6 releases more than 900 times the energy of an earthquake of magnitude 4. It's actually exactly 1,000 times the energy of an earthquake of magnitude 4. And so like an earthquake of magnitude 15 would destroy the earth. Like, I think a magnitude 15 would do it. There's a XKCD what if video about this. But yeah, actually, an earthquake of magnitude 15 would destroy the earth. So earthquakes basically go up to 9 and a bit. I think the biggest recorded was a 9.6. And yeah, it was really big earthquake. Biggest in the US was a 9.2 in Alaska in the 60s. So one significant drawback of the Richter scale is that the magnitude of the earthquake doesn't really give any indication of the damage it can cause. Because the damage caused by an earthquake is affected a lot by the properties of the surface and the construction of the area it's in. So earthquake damage depends on things like the location of the focus, the geologic rock types, population density, construction types, etc. So relatively modern quakes in areas with high populations and poor construction techniques can cause considerable property damage and loss of life. So things like the earthquake in Haiti. Earthquakes in Haiti have been really devastating because high population density, poor construction techniques, bad geologic rock types also. And then more severe quakes in sparsely populated areas can end up causing very little damage because there's just not much to damage. You know, if you have an earthquake in the middle of a big empty field, who cares? So, earthquakes less than about 3.5 in Richter magnitude are generally not felt, but they do get recorded. They're very useful scientifically. We record very small earthquakes, but they're not generally felt. 3.5 to 5.4, they're often felt, but they rarely cause much damage. Under about 6, you get at most slight damage to well-designed buildings. They can cause major damage to poorly constructed buildings over small regions. From 6.1 to 6.9, they can be destructive in areas up to about 100 kilometers from the epicenter. From 7 to 7.9, this is a major earthquake. It can cause serious damage over larger areas. And 8 or greater is a great earthquake. It can cause serious damage in areas several hundred kilometers across. Yeah, 8 or greater are the big ones. Now, the damage from earthquakes can be directly related to the vibrational tremors, or it may result from a number of secondary effects. So landslides are commonly triggered by quakes. So the 1964 Alaskan quake, much of that damage from that was due to a series of small landslides. There was a whole subdivision that broke into blocks and tilted over because basically it slid on a layer of clay that was underneath it. Fires that are initiated by initial tremors are very difficult to fight because the water lines break. So all your firefighting system infrastructure breaks. That can be very devastating. In fact, the biggest killer in earthquakes is fire. And the US government, FEMA, has literature available on earthquake preparedness. Hopefully it still does, because, yeah. And another major thing that can happen is liquefaction. During a major earthquake, wet soil basically turns into quicksand and can flow. And so you can have buildings tip over, things sink into the soil. And these are some dramatic examples of liquefaction from the Christchurch earthquake. So there's some road damage. You see that's pretty severe. 11, in New Zealand. Here we have cars sinking in due to liquefaction.
Just a couple of our family members, see if they're all right and got food and water.
Sinkholes caused by liquefaction is a major source of sinkholes and things. Things falling over.
Quite stranded, really. Roads are bad, obviously. obviously.
And really severe.
We've just come from Brisbane where they've had the floods, and I'm not sure which is the worst. But
That's already
Sure,
gone.
where we're going to go from here.
if it rock and rolls again tonight, we'll think about leaving.
Do what you always do in Canterbury, which is reach out to one another, be good neighbours, talk to one another, help each other out, do the very best you can. We will come through this.
Today, all New Zealanders grieve for you, Christchurch. Though your buildings are broken, your streets are washed, and your hearts are aching, your spirit will overcome.
So that was some examples of liquefaction, and we're at the end of the class, and that was a nice breaking point. So I will stop share.